Today I will start a new topic for stability analysis. Okay, so the topic name is root locus technique. Okay, so let's start our discussion. The main aim of a control system engineer is to design a control system that meets the desired specification. While designing the control system, it is important to determine whether his design of control system meets the desired specification or not. Okay, so this can be done by observing the response of the system for test signals. If the response does not meet the specifications, then he has to redesign the system by changing the design parameters. Moreover, the design must guarantee the stability of the system. This can be found by determining the roots of the characteristics equation. Characteristics equation is 1 plus GSHS, we have already known. So this can be, that means the stability, this can be found by determining the roots of the characteristics equation 1 plus GSHS equal to 0. For higher order system, it is a laborious process, but applying Raoult criteria to the characteristics equation, it is possible to determine whether the system is stable or unstable. But in Raoult criteria, it has certain drawbacks. So first drawback is it does not give sufficient information about relative stability of the system, that is the amount of overshoot and the settling time, etc. Sometimes poor relative stability may bring the system to the verge of instability. Second drawback is it does not help much more in design problem in which the designer is required to achieve the desired performance by varying one or more system parameters. The desired behavior of the system may be specified in terms of steady state error, peak overshoot, settling time, rise time, etc. for a step input. We have already studied that the location of closed loop system poles, that means roots of the characteristics equation, and the transient response specification are interrelated. It is frequently necessary to adjust one or more design parameters in order to obtain suitable location of roots. Therefore, it is worthwhile to determine how the roots of the characteristics equation of a given system migrate on the S-plane as one of the design parameter is adjusted. The locus of this migration is known as root locus. So once the locus is obtained, one can select the poles on the root locus which meet the desired specification and then can obtain the corresponding adjustable design parameter. That is, by adjusting the location of closed loop poles, one can obtain the desired specification. Okay, so root locus technique introduced by W.R. Evans is extensively used in design of control system. It is a graphical method for sketching the locus of roots in the S-plane as a design parameter of the system is varied. It provides the designer the sensitivity of the roots of the system to a variation in the parameter being considered. Okay. Now we will see how we will draw the locus of roots of characteristics equation. Okay. So see, consider an open loop second order type 1 system with transfer function gs equal to k divided by s into s plus p, where k is the open loop gain. The poles of open loop transfer function are at s equal to 0 and s equal to minus p. Now, the closed loop transfer function of the system is this Cs by Rs, and this is equal to k divided by s square plus ps plus 1. Okay. Now see, here I have considered unity feedback system, that means h is equal to 1. That's why the closed loop transfer function of this system is Cs by Rs equal to k divided by s square plus ps plus k. So the characteristics equation of this system is s square plus ps plus k equal to 0, and the roots are these. Okay, there are two roots because the order of the s is 2. So two roots are minus p plus minus root under p square minus 4k divided by 2. So see, from this equation we can note that for all positive values of p and k, the given second order system has its roots in the left half of S-plane. Therefore, the system is always stable for all positive values of p and k. But the relative stability of the system is decided by the location of roots, that means poles of the system. Location of poles of the system. So, the location of the roots S1 and S2 depends on the values of P and K. So, the roots or the poles the location of the roots or poles depends on the value of P and K. As P and K are varied, the roots of the characteristics equation vary, and this is both K and P are adjustable parameters. Generally, K is used in all practical systems as adjustable parameters. Adjusting K can be made by simply including an amplifier, say proportional gain or proportional controller, in series with the system. This may be the one of the reason why K is generally used as adjustable parameter. Therefore, often K, the open loop gain of the system, is varied to change the location of the poles. Okay, that is, to obtain the desired transient response, we can vary the open loop gain K while keeping the parameter P a constant. As K is varied from 0 to infinity, we can obtain the loci of the two roots or locus of the two roots S1 and S2 in the S-plane. Okay, so here we have considered three cases. So first case, see, first case is if K lies between 0 and p square by 4, that is 0 less or equal to k less p square by 4, the roots are distinct. Okay, the roots are different if k lies between 0 to p square by 4. Okay, when k equal to 0, the roots at S1 equal to 0 and S2 equal to minus p, and which is same as the poles of the open loop transfer function. So see here in this 3.13 equation, if k equal to 0, then S1 equal to 0 and S2 equal to minus p. Okay. Now, so see the case 1. Case 1 is if k varies in between 0 to p square by 4, then the roots are different. Okay, so if we take k equal to 0, then S1 is equal to 0 and S2 equal to minus p. So see this graph, this is our S domain. This is our S domain. Okay, so horizontal axis are real axis and vertical axis are imaginary axis. Okay, so see here, this is our real axis, this is our real axis, okay, and this is our imaginary axis. Okay, and this is our 0, okay, origin. This is our left hand side, this is our left hand side, and this is our right hand side. Okay, clear? Now see, let me clear this. Now see, if k equal to 0, then one root is s1 equal to 0, and if k equal to 0, first root is 0 and s2 equal to minus p. Here I have mentioned these two root by cross sign. Okay, so if k equal to 0, one root is 0 and second root is minus p. Okay, so see here, when k equal to 0, the roots are at s1 equal to 0 and s2 equal to minus p, and which is same as the poles of the open loop transfer function. Okay, we know the open loop transfer function equal to gs equal to k divided by s into s plus p. That's why for in open loop transfer function there are two root. One root is s equal to 0, another root is s minus p. So if k equal to 0, then the closed loop transfer function, in closed loop transfer function, if k equal to 0, then one root is also 0 and second root is minus p, which is same as the poles of the open loop transfer function. Okay, now see second case. Second case is when k equal to p square by 4. Okay, so when k equal to p square by 4, the roots are real and equal with the value s1 equal to s2 equal to minus p by 2. That means when k equal to p square by 4, that means two roots are equal and they are minus p by 2. Okay, so see, when k equal to p square by 4, the roots are equal. Okay, so roots are minus p by 2. Okay, so see, that is, as k starts varying from 0, that means k varied from one root, varied from this way. Okay, starting from s equal to minus p, and vary in this way, and another root starts from 0 and varied in this way. Okay, let me clear this. So see, when k equal to 0, one root is minus p by 2 and another root is 0. Okay, so and when k equal to p square by 4, so two roots are same, that is minus p by 2. That means one root start from this minus p and vary in this way, another root starts from 0 and vary in this way. Okay, so see, as k starts varying from 0, one root start moving from s1 equal to 0 and the other starts moving from s2 equal to minus p in opposite direction, and at k equal to p square by 4, both root meets at s equal to minus p by 2. Okay, clear? Now come to the, let me clear this. Now come to the third case. In third case, if k is greater than p square by 4, the roots are complex conjugate. If k is greater than p square by 4, okay, then the roots are complex conjugate and are given this, which I have given the equation number 3.13. That means if k greater than p square by 4, one root is lie here, another root is lie here. Okay, so see, let me clear this. So see here, roots are start from, one root start from this side, one root starts from minus p, another root start from 0, and they are moved in opposite direction. Okay, they meet at this point and again they go in this way. Okay, clear? Now let me clear this thing. Okay, so see, from equation 3.12 we can note that the real part of the roots are constant since p is fixed and the imaginary part varies as k varies. Therefore, the roots are moving along the vertical line, one upward and the other downward, as shown like this. Okay, so in summary, when, or we can conclude in this way, when k equal to 0, the root loci start at open loop poles S1 equal to 0 and S2 equal to minus p and move in the opposite direction as k increases. At k equal to p square by 4, the two root locus meet at minus p by 2. So they are repeated poles at minus p by 2. Okay, both roots are same. Okay, and third case, if k greater than p square by 4, the root locus move vertically in opposite direction and tends to infinity as k tends to infinity. Clear? Now see location of the roots of the characteristics equation s square plus 2s plus k. That means here I have taken p equal to 2. Okay, so see in this equation, if k is varied, see the table here, if k, we take the different values of k. So see, if k is varies in this manner, then roots are this. Okay, so see, once the root locus is obtained, it is possible to determine the variation in system performance for the variation in the parameter k. Consider the open loop transfer function gs equal to k divided by s into s plus p, and let p equal to 2. That means in this case we have taken p equal to 2. That means in this equation we take p equal to 2. So the root of the characteristics equation s square plus 2s plus k equal to 0 are determined for different values of k and are tabulated in this table. When k in between 0 to 1, the roots, so see the table, when k in between 0 to 1, the roots lie on the negative real axis. Negative real axis which correspond to overdamped response. See the table. Okay, so when k in between 0 to 1, that means 0 to 1. That means this first three. So when k in between 0 to 1, okay, the roots lie on the negative real axis, first two. So when k equal to 0, that means two roots are 0 minus 2. When k equal to 0.5, then roots are minus 0.293 minus 1.707. So when k in between 0 to 1, the roots lie on the negative real axis which correspond to overdamped response. When k equal to 1, that means this case, when k equal to 1, the roots are equal, that's are minus 1. Okay, and this correspond to a critically damped system. And next case is for k greater than 1, that means this case. Okay, so see, for k greater than 1, the roots are complex conjugate and this correspond to an underdamped system. Okay, see, in this way, we can draw the locus of the roots by varying one parameter or varying the parameter k, that means open loop gain. Okay. Now come to even condition. What is even conditions? Let us consider a system with open loop transfer function Gs and feedback transfer function Hs. Then the closed loop transfer function is Ts equal to Gs divided by 1 plus GSHs, and the characteristics equation of this system is 1 plus GSHs equal to 0. Now let Ps equal to Gs plus Hs. That's why if we put Ps in our characteristics equation, then our characteristics equation is 1 plus Ps equal to 0. So from this equation we can write Ps equal to minus 1. Since S is a complex variable, and we can write the characteristics equation as follows. That means magnitude is equal to 1. This is magnitude criteria. Mod of Ps equal to 1. This is magnitude criteria. And another one is angle criteria. That means angle of Ps equal to plus minus 2q plus 1 into 180 degree, where q is equal to 0, 1, 2, 3 like this. Okay. So these two equations, that means 3.19 equation and 3.20 equation, these two equations are known as even conditions. Okay, using this equation, means these two equation, we can define the locus. Okay, so the set of all points on the S plane that satisfy the angle criteria, that means equation number 3.20, is on the root locus. Okay, the set of all points on the S plane that satisfy the angle criteria is on the root locus. The magnitude criteria, that means equation 3.19, gives the value of k corresponding to a point on the locus. So this is our even condition. Okay, so to draw the root locus, first satisfy these two conditions. First is magnitude criteria, second one is angle criteria. So for angle criteria, the set of all points on the S plane that satisfy the angle criteria is on the root locus. The magnitude criteria gives the value of k corresponding to a point on the locus. Okay. So the rest part of this root locus I will be discussed in the next lecture. Okay.